Hello everyone, welcome back to the another session in design and analysis of algorithms. Today we'll be going to talk about n queens problem using backtracking. This topic is from 4th unit, topic number 2. So as far as this video is concerned, we'll be going to talk about what is n queens problem, the standard problem, n queens problem, and we'll take the example of 4 queens problem, and also we'll see the solution for 8 queens problem and how to apply backtracking to solve n queen problem. So these are the things what I'm going to talk in this video. Now let's get started. N queens problem. It is a generalization of the 4 queen problem or 8 queens problem. N queens are to be placed on an n by n chessboard so that no 2 queens under attack. That is, no 2 queens are on the same row, same column and same diagonal. That means if you take, now it is a 4 by 4 chessboard. If I wanted to place a queen, I have 4 queens to place in the chessboard or in this n by n board. So if I wanted to place q1 over here, so I should not place second queen in this row, in the column, in this diagonal, and anywhere else I can place. So q2 I can place over here. Keeping in mind, if I place any other queen, q3, q4, that should not be under attack. So this is what n queens problem. Generalizing our earlier discussion, the solution space consists of all n factorial permutations of the n tuple 1, 2, 3 up to n. So we were discussed in the previous example how backtracking state space tree can get constructed. Now, a standard chessboard will be of 8 by 8, but we are using a size of a problem, we have taken 4 by 4 and 4 queens are given. So in a game of chessboard, most of us will love to play chessboard, right? In a game of chessboard, queen will be there, which will have its move like horizontal, and that is in row or column or diagonally it moves. So here also the same rule will follow, and that queen we have to place them on this board. All 4 queens we have to place such that no 2 queens are under attack. Attack means what? Those queens should not be in the same row, same column and same diagonal. So this is what queens are not under attack. So when do you say they are under attack? When they found in same row or else column or else diagonal, then it will be an under attack. So we have to make sure that the queens are not under attack. Now, so for this we have more than one solution and we want all those solutions. If you want only one solution for this problem, that is called as optimization, whereas you can apply dynamic programming or greedy method. But I told you just the moment that I need all the solutions for placing the queens, there is no attack. So that means when I'm looking at all the solutions, all the possible solutions, I'm using what? Backtracking with brute force approach. Now, I can place 4 queens over here. So how many how many permutations I'll be having? 16c4. To reduce this problem, it's a big problem, right? That I have to see that in this board, when I wanted to place this 4 queens in this board, I will be having a huge problem of placing the queens for these many combinations. To reduce the problem, we'll put one condition or one constraint, that is first queen should be in any of the column of first row. Second queen should be in any of the column of second row, keeping in the mind the constraint no same row, same column. Right? So row we are taking care. Row means what? Now we are having a word that You cannot place on the same row. Let's suppose that q1 is placed over here. Q1 has to be placed only in the first row. Q1 should not come to this row. If Q1 can also come into the second or third or fourth, your combinations possibilities are more. To reduce these possibilities, we are bringing a condition that first queen should be in the first row itself. In any of the column, with satisfying this constraint. So second row is for Q2, third row is for Q3, fourth row is for Q4. Now, this array will help you out to know which queen is allotted for which column. Now, first queen should be in anywhere in the first row and likewise, and we will write the column number here in this array. We'll try to avoid keeping the queens in same column. For this, we'll be going to draw state space tree. Now I'm taking state space tree. So as far as state space tree is considered, now I'll take again this chessboard board. So when I told it is a chessboard, you will ask me where is 8x8 board, correct? So that's what I'm using. It is 4x4 board. Now it's 1 2 3 4 1 2 3 4, correct? Now, so the first possibility will be checking that x1 is equal to 1. This is my first possibility. Means what? That I wanted to place first queen in the first column. I'll change the ink. First queen is in the first column. So now it is fixed. That means I cannot find any attack as it is my first move. Now, so come to second one. Now second is what? I am placing the x2 queen. That is second queen in the second column. Second queen in the second column. That means here Q2. So no same row, no same column. We were taking the precaution, but as of now I am not considering the diagonal. I'll let you know once after I finish all these possibilities. So now Q2 is I fixed. Okay. Now let's go and see the third queen. Third queen I fixed at third column. x3 is equal to 3. That means Q3 over here. And x4 is equal to 4 and 4. So this is one of the possibility. Now here only two constraints were satisfied. No same row, no same column, but diagonal. So diagonal, the attack is there, but I'm not including this constraint into here for this solution to see how many number of nodes I can generate. Right? Now it is under attack. So what I'm going to do, I'm taking out this Q4 from here. So there is no place of placing Q4. So I'm going backtrack. Q4 cannot move further because it is the last cell. So what I'm going backtrack. Backtrack is what? I wanted to change the place of Q3. So where I'm changing the Q3 place? I'm changing the Q3 place to Q4. That means x3. Third queen is going to be occupy fourth place, fourth column. That means Q3 come here. So Q3 is here and Q4 will be here. That's what I did here. x4 is equal to 3. Now again, see that any possibility, do you have any other possibilities that where we have an attack? Q2 is under attack. So what we'll do, again go back for what? So now we'll be going for x2. Now it is in under attack. What? Now change the place of this Q2 to somewhere. So where we have to go, I'm just going to the third place. Now x2 is at third place. Now I'm making x2. That is queen 2 in the third place. Queen 2 in the third place. Now queen 2 is in the third place. Q3 is here and Q4 is here. Now diagonally under attack. So again I have to change the place of what? So now again I have to change the place of Q3. So again now come down. x3, that third queen, I am changing to second place. Okay. I am changing to second place. Now again x4 to fourth place I am changing. Now let's see any attack over here. Yes, it is. Again these two will get under attack. Now again go backtrack. backtrack and change the place of x4 is equal to 4 and the place of x3 is 2. Now still is there any under attack? Yes. Now x2 element is an under attack. Now what we'll do, again change the place of x2 to 4. Now this time x2, that queen 2 is going to be occupy the 4th place. So when it is x2 is equal to 4, now again proportional to it these queens will get changed because those are under attack. Now we'll change this to 2 and 3 and vice 3 to 2. Now it is one possibility where my queens are not under attack. So now come to here. Q2, Q3, Q4 were settled. Now compare with Q1. Now it is an under attack. Now change Q1 place. To change Q1 place, I am just moving further. So how many nodes like this I can generate? Now this is the formula to know how many nodes you will get. So what is the formula? This formula is that I am taking 4 queens that started with I equal to 0 to 3. So now j is equal to 0 to I, it is 4 minus j. If you substitute and calculate, now let's see. Before I go to this formula, we'll take a manual calculation. So under one node, under this, let's suppose it is 1. Under 1, how many possibilities? 4, right? x1 can be placed to 1, x2 can be placed to x1 can be placed to second column, x1 can be placed to third column, x1 can be placed to fourth column. So under 1, how many possibilities you have? 4 nodes plus. Now come, we are just calculating the number of nodes. So come here. Now under this, how many nodes you have? 3. That means 4 into 3 plus. Again come down, 1 into. Here 1, 2, 3, 4. Each is having 3. That means 4 nodes will have 3. 4 into 3. Now come down. 4 into 3 into 2 plus 4 into 3 into 2 into 1. This is what the sum of nodes. Product of sum of nodes. So finally it is 1 into 4. 4 plus 4 3s are 12 plus 24 plus 24. So put together you will get 65 is the answer. So total number of nodes of the state space tree will be 65. So this is what actually possible solutions of this. Now we are putting a condition. The condition is what? Bounding condition. Now I am putting some bounding condition. What is bounding condition? Bounding condition is what? We will kill the node when it is diagonally have an attack. Either it is row or it is column or it is diagonal. We'll kill the node and will not extract further. That is what bounding function. Now let's see the bound. With the bounding function I am explaining. Now the same. Take some board. 1, 2, 3, 4. 1, 2, 3, 4. Now I wanted to place Q1 over here. Now it is Q1 place. So where did I place it Q1? In x1 is equal to 1. That means my first queen is at first column. Now move further because no attack, as we did not have any other queens in the picture. We don't have any attack. It is the first queen. Now move further. x2 is equal to 2. My second queen I am placing in the place of second column. Now what happened? Diagonally these are under attack. Now what you have to do? You have to kill this node. So there should not be any extraction further. You are killing here itself. So what we'll do? This is not a safe place. This is not the safe place for Q2 to keep. What we'll do? We'll go back. We'll go back. That is backtrack. Backtrack and change the place of x2 from 2 to 3. Now I'm just changing this place and I'm moving Q2 to third column. x2 is equal to 3. Now let's see. Q2 has placed with no attack with Q1. Now again find the place of Q3. Now I am placing the third queen in the second column. Now I am placing over here. Do they have any under attack? Yes, Q2 and Q3 under attack. Now again kill the node because there is no extraction. There should not be any extraction as you have an attack in between Q2 and Q3. So kill the node and again backtrack. Backtrack where you are going. Backtrack and you are going to the place of x2, correct? Now there will be other node. The other node is what? Now x2 is equal to 4. Now x2 is equal to 4. Now what happens in x2 is equal to 4? Again x2 4 in the sense q2 has changed its place from the third column to fourth column. Now what happens in x2 is equal to 4? So again change. Now one is first queen is at first column, second queen is at fourth column, and third queen is at second column. Third queen is at second column. And so when it is in the second column, again for q4 I am putting in q third column. Now these two are under attack. What to do? Again kill the node. So again go back to the solution to find out. If you do so, you will find the right places where no queen is under attack. That the place are q1 has to be in second column, second row, q2 should be in fourth column. These are the places. q1 in second column, q2 in fourth column, q3 in first column, q4 is third column. These are the right places where you will not find any attack. No same row, no same column, no same diagonal. And there is one more solution, that is what mirror image of the same. That q1, q2, q3, q4. That is 3, 1, 4, 2. So this is about 4 queen problem. If you follow the same principle for 8 queen problem, you will find this solution for 8 queen problem. Okay. So this is about n queens problem. I have explained you how to construct state space tree, what are the possible number of nodes through the formula, and keeping in the mind the constraints of no row, no same row, no same column, no same diagonal. Use bounding function and kill the nodes, and no extraction further. So this is about n queens problem. Thank you all.